Load factor is the ratio of the maximum load an aircraft can sustain to the gross weight of the aircraft. The load factor is measured in G's, which is the acceleration of gravity. If an aircraft is pulled up from a dive, subjecting the pilot to 3 G's, he or she would be pressed down into the seat with a force equal to 3 times his or her weight. Load factors are important for 2 reasons. It is possible for a pilot to impose a dangerous overload on the aircraft's structures, and an increased load factor increases the stalling speed and makes stalls possible at seemingly safe flight speeds. In a constant altitude, coordinated turn in any aircraft, the load factor is the result of 2 forces, centrifugal force and gravity. To maintain altitude during a turn, the aircraft must sustain the loads shown at the chart on the right. The maximum bank for the average general aviation aircraft is 60 degrees. When an aircraft experiences a load, as in a turn, the speed at which the aircraft stalls increases. This means that an aircraft with a normal unaccelerated stalling speed of 50 knots can be stalled at 100 knots by inducing a load factor of 4 Gs. The maximum speed at which an aircraft may be stalled safely is now determined for all new designs. This speed is called the design maneuvering speed, or VA. A thorough knowledge of load factors induced by varying degrees of bank and the VA aids in the prevention of 2 of the most serious types of accidents: stalls from steep turns or excessively maneuvering near the ground, and structural failures during acrobatics or other violent maneuvers resulting from loss of control. Relatively high load factors can be experienced in the following flight maneuvers: turns, stalls, spins, high-speed stalls, chandelles, which is a maximum power 180-degree climbing turn, lazy eights, which involve tracing the nose through a figure 8 pattern, and rough air. Care should be exerted in these situations by the pilot to ensure that load limits are never reached. The flight operating strength of an aircraft is presented on a graph whose vertical scale is based on load factor. The diagram is called a VG diagram, or velocity versus G loads or load factor. Each aircraft has its own VG diagram, which is valid at a certain weight and altitude. For any given load factor, a straight line may be drawn across the diagram to see at which airspeed certain operating ranges exist. Also, for certain airspeeds, the load factor can be checked at certain levels negative and positive. For example, if you wanted to know how many G-forces you could exert on the aircraft at 160 miles per hour indicated airspeed, you would find on the bottom of the diagram 160 and then draw a line straight up to see that any load under -2 and any load above 4.2 will cause structural damage to this aircraft according to its VG diagram. An airplane's bank angle and speed affect how quickly and in what distance it can turn. In the above example, 2 planes enter a canyon. They both bank the same amount, but one aircraft is traveling 20 knots faster than the other. The result is a larger turning radius for the faster aircraft. That aircraft will not be able to make it out of the canyon traveling at its given speed. The way to correct this would be to either bank more or to slow down to shorten the radius of the turn. Weight and balance is very important in any pre-flight. Pilots often overlook weight and balance calculations, which leads to an unknown center of gravity. As stressed earlier in the lesson, a center of gravity that is positioned in the wrong place on an aircraft causes accidents. Other things to consider are gross weight. Even if the center of gravity of the aircraft has not been displaced outside the envelope, the gross weight may be too high for the aircraft. Overloading the aircraft's structure can cause serious damage to the aircraft, and even small overloads can build up into larger damage. As shown above, a higher gross weight causes the aircraft to behave differently and change its flight characteristics. In subsonic aerodynamics, the theory of lift is based upon the forces generated on a body and a moving gas, air, in which it is immersed. At speeds of approximately 260 knots, air can be considered incompressible, in that, at a fixed altitude, its density remains nearly constant, while its pressure varies. Even when an aircraft is traveling slower than the speed of sound, the air over the wing may be traveling faster than the speed of sound. The speed of sound is labeled as Mach 1. Twice the speed of sound would be written as Mach 2, and half the speed of sound would be written as Mach 0.5. The above pictures show the points where this happens and also the resulting drag. Mach speed is always given in relation to the aircraft's actual speed through the air and not the indicated airspeed. When an aircraft flies at subsonic speeds, the air in front of the wing acts to warn the air around it that it's going to be separated. When it occurs, the air is able to move out of the way and easily let the wing pass through. However, when speeds increase to speeds more than the speed of sound, this cushion of air does not warn the oncoming air quickly enough to get out of the way. Having had no advanced warning of the airplane's approach, and in the next instant the same air particles are forced to undergo sudden and drastic changes in temperature, pressure, density, and velocity. The boundary between the undisturbed air and the region of compressed air is called a shock or compression wave. The above picture shows the transition from just before to during the formation of a compression wave on a wing. One side effect to high-speed flight is that the flight controls become harder to control because of airflow over the wing causing separation. To counteract this, wings are often swept back on aircraft that make constant transonic flights. This design tricks the wing into thinking it is flying slower than it is because the wind is not hitting the leading edge at 90 degrees. This helps to delay the formation of shock waves. One problem, however, with the swept-back design is that the wing tends to stall at the tip first rather than the wing root, which reduces the aileron's effectiveness during a stall. The stall situation could be made worse by a T-tail configuration, which affords little or no pre-stall warning in the form of tail control surface buffet. Shown above, the T-tail, being above the wing wake, remains effective even after the wing has begun to stall, allowing the pilot to inadvertently drive the wing into a deeper stall at a much greater angle of attack. If the horizontal tail surfaces then become buried in the wing's wake, the elevator may lose all effectiveness, making it impossible to reduce pitch attitude and break the stall. Things like stick pushers, which automatically push the nose forward, and a stick shaker, which gives the pilots a warning of the stall, both help to reduce the risk of this situation from ever developing. On high-speed aircraft, flight controls are divided into primary flight controls and secondary or auxiliary flight controls. The primary flight controls maneuver the aircraft about the pitch, roll, and yaw axes. They include the ailerons, elevator, and rudder. Secondary or auxiliary flight controls include tabs, leading-edge flaps, trailing-edge flaps, spoilers, and slats. Spoilers are used as speed brakes to slow down high-speed aircraft. They can also be used to help turn the aircraft because the ailerons are quite small. Leading-edge slots, slats, and flaps are used to improve the low-speed characteristics during takeoff, climb, and landing. These devices can provide on average a 50-knot reduction in the stall speed of an aircraft. The tail uses a stabilizer as well as an elevator to allow the elevator to rest in the neutral position and have full deflection in either direction even when the aircraft is trimmed. Because of the size and high speeds of jet transport aircraft, the forces required to move the control surfaces can be beyond the strength of the pilot. Consequently, the control surfaces are actuated by hydraulic or electrical power units. Please help us spread the word about Pilot Training System, and we look forward to further servicing your flight training needs.